we will go to the fifth and last lecture of week 3 of this course. In this lecture, I will review what we learnt in week 3 and do a practice question. So, we will review week 3 and do practice questions. Now, in week 3, we learnt about symmetries in crystals, and in particular we learnt about point symmetries. Okay. I will mention here that the translational symmetries will be discussed in week 4. Then we discussed the different point symmetry elements and the symmetry operations. We talked about two kinds of notations, the Schoenflies and the Hermann-Mauguin notations for symmetry operations. And then at the end, we came back to fractional coordinates and talked about planar visualization of crystals. Now, to understand symmetries in crystals better, it is always good to look at examples. Okay. And now today I am going to take an example of a diamond lattice or the diamond crystal that we studied in the last lecture. Okay. And what I am going to try to do is to, your question is to list all the point symmetries of the diamond lattice and give the Hermann-Mauguin notations for them. Okay. And it will turn out that this exercise will turn out to be non-trivial. Okay. What you should keep in mind is that a lattice is infinite. Okay. That means it stretches to infinity in all directions. Okay. And we are listing only the point symmetries. Okay. Now, again the word point in this context, okay, just refers to symmetries of the unit cell, and point in this context refers to those symmetries which are not translational symmetries. Okay. So, it is point in the sense of not translational . And also we should keep in mind that two things keep in mind, diamond lattice is not a Bravais lattice, and the other thing to keep in mind, which you can see from here, is that this unit cell, okay, or the conventional unit cell, that is the diamond cell shown as a cube. Okay. This has a total of 8 atoms. Okay. There are 4 due to the FCC and 4 due to these green atoms at the tetrahedral voids. Okay. So, it has a total of 8 atoms in this conventional cell. Okay. So, clearly it is not a primitive cell. Okay. And in fact, this cell does not even have all the symmetries of the diamond lattice. Okay. So, these are things to be kept in mind. So, you should always look at lattice as an infinite infinite set of points. That means it extends in all directions, and you should also keep in mind that this is a convenient unit cell that is used to represent the diamond lattice. Okay. So, now let us go to the symmetry elements. So, let us look at the rotational symmetry elements, okay, and this will turn out to be highly non-trivial. Okay. Now, we had seen that a cube, you remember a cube had these 4, it was characterized by 4 C3 axes and 3 C4 axis. Okay. So, remember in a cube, okay, so in a cube, okay, you had 4 C3 axis and 3 C4 axis. Okay. The 3 C4 axis were the ones that were going through the center of the face, okay, like this, and going all the way and coming out from the other side through the center of this face. Okay. So I'll just show these. Okay. So this is an example of a C4 axis. Okay. This is the C4 axis of the cube. Okay. So for a cube, this is a C4 axis for cube. Okay. And this is the C2 axis for the cube. Okay. And there are 3 of these. So there is one in the z direction, one in the x direction, and one in the y direction. Okay. Now you can already see that some of these will not be the same axis anymore. Okay. So and to see this, it's convenient to go back to the fractional coordinates that we discussed in the last lecture. So let's show the fractional coordinates. So this is at z equal to 0, then you have z equal to 1 by 4, you had these 2 points at 1 by 4. Okay. And at 3 by 4 you had these 2 points, and you had all these 6 points at half. Okay. And the remaining points were at z equal, the corner and the face center were at z equal to 0. Okay. So this is the planar representation, and now you can see that if I let's look at this. Oh, this should be C4. Sorry, this is a mistake. This should be C4 for a cube. I have made a couple of mistakes. Okay, this should be C3 for a cube, and this should be C4 for a cube. Okay, so the 4 C3s. Okay, this is a C3 for a cube. This is a C4 for a cube. Now what happens to this? Let's look at the C4. Okay, now you can see that the C4 axis, okay, and if you look in a plane, okay, so if you are looking at this C4, you can see this plane, and in this planar representation you can see that C4 will take any of these points located at 1/4 and move it directly below the point that is located at 3 by 4. Okay, so if you do a C4, okay, if you do a C4, and in particular this is along the z direction, okay, then what you will get is, and I will just show it, the corners. I'll show it a little smaller. Okay, don't be. So you have the corner atoms, you have the face center, and now this 1/4 actually comes here. So these are the 2 1/4s. Okay, remember C4 will not change the z coordinate, and these are the 2 3/4. So in the plane, the location of the 1/4 and 3/4 are changed. Okay, so clearly there is no C4 axis in this diamond lattice. However, if you do C4 twice, okay, then you can then you will get back to exactly something like this, because the two points that are located at z equal to 3/4 will swap. The points that are located at z equal to 1/4 will swap. So clearly you have 3 C2 axis. Okay, this is directly due to the cube. Okay, now the 4 3-fold rotations, okay, they are also symmetry operations for a diamond lattice. Okay, so you still have 4 C3 axis. So these are the axes along the body diagonals. Okay. Now let's look at this 4 C3 axis along the body diagonals once again. Okay. Now if you do a C3 operation, okay, along about the body diagonal, okay. Now what we said is that will actually, if you are doing along, if you consider this C3 axis, okay, then the corner atoms, which are represented by 1, 2, 1, 2 and 3 will get exchanged with each other. Okay. And now this will actually and this will cause an exchange of these 3 atoms. So these 3 atoms, which are tetrahedrally located with respect to this corner atom, will get exchanged. So there are 4 C3 axes in the diamond lattice. Okay. In fact, what is interesting about the diamond lattice is that the coordination number equal to 4. Okay. So in a diamond lattice, okay, again we will see this in more detail, but the number of nearest neighbors for any atom is 4. Okay. This is a property of the diamond lattice, and you can see this, you can easily take any atom and show that it has 4 nearest neighbors. Okay. So this is the number of nearest neighbors. So it is a number of atoms that are closest to it. So if you take, for example, if you take this atom, this atom in green, okay, so that has 4 neighbors, these 1, 2, 3 and 4. So these 4 are nearest neighbors to this green atom. Okay. So in other words, if the green atom was this atom, okay, so it has 4 nearest neighbors, okay, and those nearest neighbors, I will show them in light blue here. So they will be this and this. Yes, this. These will be the 4 nearest neighbors of this atom. Okay. So the coordination number is just 4. Okay. Now so we have the 3 C2 axis and the 4 C3 axis. Now in a cube there are other symmetries. Okay. One, there are actually 6 other C2 axes. Okay. Those 6 C2 axes of a cube, okay, those go from so they go from through the edges, okay, through one edge and the diametrically opposite edge. Okay. So this axis that goes from the center of one edge to the center of the diametrically opposite edge, okay, this in a cube, this is a C2 axis. Okay. So this C2 axis in the cube is also there in the diamond lattice. So there are an additional 6 C2 axis. Okay. So we end up with a total of 9 C2 axis. You have 4 C3 axis. Okay. And the question is that all that are there with the rotations? Okay. And the answer is no. Okay. So what was the C4 axis in a cube, okay, that becomes an S4 axis. So the C4 axis of the cube becomes an S4 axis of a cube. Okay, so there are 4 S4 axis, or rather let me use 4 bar axis. Okay, 4 bar means you rotate it and you invert about the center. Okay, so if you do that, you can clearly see that if you rotate it by 90 degrees, okay, then this this point will come somewhere here. Okay, then you flip it about the center and it will come on top of this point. You invert it around the center. Okay, so this is inversion around, this is rotation by 90 degrees followed by inversion about the center. Okay, so there are total of 9 C2 axis, 4 C3 axis, and 4 and sorry, it should not be 4, it should be 3. So there are 3 4 bar axis. Okay, so the four-fold rotation axis are actually inversion axis. So in the Hermann-Maugeot notation, you have 9 2 rotations. Okay, so you have 9 of these 2s. This is 2-fold rotations. You have 3 of 4 bar. This is roto-inversions. This is 4-fold roto-inversions. And finally, you have 4 3 axis, that is 3-fold rotation. Okay, so these are all the rotation axes that are present in the diamond lattice. Okay, now next let us go to the reflection symmetry. So the reflection symmetries are shown in this figure. Okay, so if we look at this 2D planar representation that is seen here on the right, okay, we can immediately see that there are 2 mirrors, okay, along these diagonals. So these are shown in light blue color. Okay, now recall that in the case of a cube, you had 2 additional mirrors which I'll show in this purple color, which are not there in the case of the diamond lattice. So this was a mirror in the case of a cube, and the corresponding perpendicular one. So these were mirrors in the case of a cube. So this is not a mirror for diamond lattice. So this is mirror plane of cube, but not a diamond. Okay, so this is not a mirror plane for diamond, this is not a mirror plane of diamond. Okay, so these 2 mirror planes of the cube are not mirror planes in diamond. However, these 2 other planes shown in light blue, these are mirror planes. Okay, so now this planar representation is in the xy plane. Okay, and it is in the xy plane, and so you will have similar representations in the xz and yz plane. Okay, so so clearly you will get a total of 2 into 3 6 mirror planes, okay, from which correspond to these diagonals. Okay, so there are 6 mirror planes corresponding to these diagonals shown in light blue. Okay, so 2 in the xy, 2 in the xz, and 2 in the yz. Okay, so here I have on the cube I have shown one of these planes, what it looks like. Okay, so this is one of these diagonal planes. Okay, now what are the other planes? Okay, it turns out that there are 3 more planes, 3 more unique planes in the case of a diamond lattice. Okay, and these three planes I will just show. So, there will be one in the xy plane, you will see one another mirror plane. I will show this in orange. Okay. Now, you can see that this is a mirror plane of reflection. What I have shown in this color is a mirror plane of reflection. Okay. And to see this, you have to extend the crystal. Okay. So you will extend the crystal. So, let us put another red point here, another red point here, okay, and we will put a blue point here. Okay. Notice that you are translating the same crystal here, okay, and you will have a black point here. Okay. I am just showing this this top right corner of the crystal, and you can already see that this is a mirror plane. So, so the point is, this will be a plane of, this will be a mirror plane. Okay. So, I just repeated this entire unit cell, okay, just to emphasize that now you can clearly see that this is a plane of symmetry. So, what I have shown in orange is a plane of symmetry. Okay. And let me just show the original unit cell in yellow, okay, just to emphasize that we had to extend the unit cell to see this symmetry operation. So, because and the way we extended it was we just translated it. Okay. So, because of the translational symmetry of the cube, you could just extend it and you could see the same cell. Okay. Now, what is also important to note here is the following. There is a little subtlety. So, if you take this mirror plane which I have shown in orange, okay, now this is in the xy plane, okay, so there should be one in the yz and one in the xz plane. So, you will get 3 more mirror planes. Okay. So, so that gives a total of 9 mirror planes, and in fact the diamond lattice has 9 mirror planes, but there is a little subtlety here, okay, and that is the following. Okay. The subtlety has to do with the fact that we considered only one of these planes. Okay. Now, you could consider other planes. For example, let me show this. You could consider a plane like this. This is also a mirror plane. Similarly, you could consider a plane like this. This would also be a mirror plane. Okay. So these planes in green that are shown in green would also be mirror planes. Okay. However, when we count the number of mirror planes, we only count the plane in brown. Okay. We do not consider the planes in green. Okay. And the reason for this is slightly subtle. Okay. So the first point to note is that these are the green ones are also mirror planes. However, in the usual way of counting the number of mirror planes for a diamond lattice, we do not count these green ones. Okay. So the reason these are not counted is actually quite subtle. Okay. So keep in mind that the diamond lattice is not a primitive lattice. Okay. So diamond, in fact, it's not even a Bravais lattice, but essentially this diamond cubic unit cell is not primitive. Okay. So it's not primitive, and so it's not primitive in the sense it contains 8 atoms. And so what we want to say is that this small unit that is shown here, that I have shaded this unit, okay, this is 1/8 of the cell. Okay, this is 1/8 of the cell. Okay, and it turns out that that you only need to consider the mirror operation on this 1/8 of the cell. Okay, and this is because your unit cell is not primitive. Okay, and so this is the asymmetric unit of this cell. Okay, this might be a little complicated. Okay, and in fact these are the unique mirror planes. Okay, these three mirror planes, these additional 3 mirror planes are the unique mirror planes. Okay, so it might seem a little complicated, but this is something to keep in mind. Okay, it's something to keep in mind. Okay, that your diamond is not this unit cell is not primitive. It has 8 atoms. Okay, so if you have just one atom, okay, so you take 1/8 of this cell, okay, then by symmetry operations you should be able to generate the entire cell. So what it means is that you only consider this 1/8 for all the operations. Okay, so this is something to be kept in mind, that it's not always easy to count the number of unique symmetry elements. Okay, but nevertheless, irrespective of that, it is true that these lines in green, okay, on this unit cell are also symmetry operations. Okay, so they are also mirror planes. Okay, so we have all these mirror planes, but the number of unique mirror planes is just 3. Okay, so next we go to the center of inversion. Okay, so the diamond lattice has a center of inversion. Now if you take the center point of this diamond lattice, okay, so that is the central atom. Actually there is no atom at the center of this cube, but if you take the center of this cube, okay, if you take the center of the cube, okay, and you invert about that point, okay, then what will happen is an atom at height 3/4 will become an atom at height 1/4. Okay, and if you go through the whole exercise, you will see that inversion about this center point. The center point has coordinates half, half, half. Okay, so the coordinates of the center point are fractional coordinates are half, half, half. So if you do an inversion about the center point, okay, then you will get a crystal that looks different from what you started with, in the following sense. So you had the blue points which were at z equal to 1/4 along the body diagonal going in this direction. Now you have the green points at height 3/4 along this body diagonal. Okay, so clearly half, half, half is not an inversion center. Okay, however, again you can see this by extending the cell. You can see that there is an inversion center located at this point, which is shown in this violet color. Okay, this point shown in violet color is an inversion center. So there is an inversion center at 1/8, 1/8 and 1/8. So the coordinates of this point on this cell, you can see it lies right here. Okay, so since this green atom was at coordinates of 1/4, 1/4, 1/4, this is a midway point between 0, 0, 0 and 1/4, 1/4, 1/4. So this is 0, 0, 0. This green atom is 1/4, 1/4, 1/4. Okay, and this point midway between these will have coordinates of 1 by 8, 1 by 8, 1 by 8, and you can again look at the entire crystal and show that this point is actually an inversion center. Okay. Again remember, so when you invert about this point, clearly the point at 0 0 0 and 1 4 1 4 1 4 will swap each other. Okay. And you can show that you will generate the entire crystal in this way. Okay. Again, inversion is not a very easy operation to visualize. Okay. However, you can easily extend the unit cell and see this. Okay. Now again there are several other inversion centers. Okay. If this is an inversion center, you could have inversion centers at midpoints of all these atoms. Okay. So there are several other inversion centers which are again not shown. Okay. Because of the reasons we mentioned the last time, that you only need to consider the asymmetric unit to show the inversion center. So once again, you keep in mind that we will only show the inversion center in this small unit. Okay. Again it is a fact that there are several other inversion centers. Okay. And you know, I won't mention, in fact each of these points in between these dots will be an inversion center. Okay. So if you take any point bisecting any nearest neighbor, any pair of nearest neighbor atoms, okay, that will be an inversion center. Okay. So finally we will come back to the Rotoinversions. Now we already talked about the Rotoinversions. Okay. We said that each of these C2 axis is actually an S4 axis. Okay. So it is or a 4-bar axis. So there are 3 Rotoinversions in the diamond lattice. Okay. So one will be in this direction, one will be in this direction. Okay. So these two are in the plane of the paper, and then one is perpendicular to the plane of the paper, that is this direction. Okay. So with that we have completed the identification of all the point symmetry elements and all the point symmetry operations of the diamond lattice. Okay. And this concludes our discussion on point symmetry elements, and it concludes week 3 of this course. Next week we will look at the translational symmetry elements. Thank you.